And then you can look at, this is the Iterative Ensemble Smoother, and they are both of the analytic and the ensemble representations are much more similar to the theoretical value, so you have a big improvement. For this, no, something is going, let's see. Yeah, for ESMDA, it's even better than for this particular case. That is not what we see in general. For other applications, then Iterative Ensemble Smoother gives a better result. So it's, but here and these are the results for the Ensemble Smoother with 2 steps, 4 steps, 8 steps, 16 steps, and 32 steps. Or actually 128. But it means that you need like 16 to 32 steps with MDA for it to really converge. When we talk about nonlinearity, I'm going to show quickly some plots that illustrates what we are trying to deal with or handle with these ensemble methods. And I created an artificial case again with, my model is this one, so it has a sine function in it. And this means that for one y, there may be many values of x. So it's a multimodal system. But then multimodality is not necessarily a problem unless your prior covers many modes, right? If you have a really narrow prior, then you might be in one mode and things behaves almost linearly. And that's what I try to illustrate here. So I created 3 cases with different priors. So you have a narrow one where all the prior realizations are contained in the central mode. They have a kind of second prior, which has realizations in the second modes as well, and then a wide one, which has actually have realizations in 5 modes. And I wanted to see what the different methods are doing in the different cases and what the impact of introducing these ensemble gradients are. And so I have both the analytic and the ensemble gradients. For the ensemble smoother with case 1, where I have the narrow prior, you see that the model response is almost linear. And this is the Bayesian posterior, so what I'm trying to solve for. And you see that ensemble smoother with ensemble representation or analytic representation all give exactly the same result. So you manage, this problem is linear enough for the ensemble smoother to work. And the ESMDA and IES also give very similar results. So all the methods are working and handling this case. If you go to the second case, then I have solutions in, most of them are in the central mode, but I also have some realizations in the secondary modes. And we see that the ensemble smoother is not able to recover it. It's kind of smeared out, and it's because the gradient you use is the same for all the realizations, and but it's a hard problem to solve in this case. If you go to ESMDA, you are recovering the central mode, but for some reason with the analytic representation of the gradient, it doesn't work. If you go to iterative ensemble smoothers, then with the ensemble realizations, you get, or ensemble representation, you get the central mode. With the analytic representation, you get the theoretical solution. So in this case, it actually works quite well. And this actually corresponds, I believe, to what you will do, for example, at ESMWF, where you are using adjoints and iterations to compute these gradients. I think you are more in this representation than this one. I'm not sure, but that was my understanding. And finally, in this highly nonlinear case, none of the ensemble methods will work, but iterative ensemble smoother with analytic gradients will again find a theoretical solution, which is quite good. Then I'm going to show a couple of slides about model errors and the importance of model errors. And this is something I've been kind of thinking about for quite some time, and it was not really clear to me how to incorporate the model errors in the iterative smoothers and if it was possible. But then, as we saw from the initial slides, it was quite easy. You just lump it together with the rest of the unknowns. But again, you estimate the errors in the same way as you estimate any other state variable, and you have to integrate your model with the updated estimates of model errors and when you compute the final solution. So it's again the same equations as before, but now my state dimension is 2 instead of 1. So I added this q here, which is the model error. And if you look at what happens, this is the case without model errors, and it's the linear case. So you have the prior, we have the posterior again, and you combine it with the likelihood, you update here, and you make a new prediction. If you introduce the model errors, what happens first is that it's what you would expect, because now your prediction has a larger variance. So you get stronger impact from the likelihood. You move the posterior towards the measurements. But what we actually do now is that we make this prediction, and then we update the prior here. And we see that the update of the prior is weaker. And that's because you are adding noise to your prediction. So you reduce the correlations between the prediction and the prior. And still, the update of the posterior is stronger. So how is that happening? And that's really because you also estimate the model errors, and when you update this one and you compute your final update, you force your equations with the estimated model errors. And if you look at the estimate of model errors, you have the prior, which is centered at 0, and you introduce this negative bias. So it just shows that you can estimate the model errors in the same way as you estimate the other state variables or parameters. But when you compute the final update, you need to use these updated estimates to force your model. And then you get a result that's totally consistent with Bayes. And I have the same plots for the nonlinear case, but I'm not going to, they just show the same behavior. Except now the different methods are giving different estimates, but slightly different estimates. Okay. I'm going to spend, I see I have a bit time left, yes. I'm going to spend some time, 20 minutes almost. Yeah. It's counting up, yeah. Okay, so this is a paper. It's finished. It's put on archive, but it was done yesterday, so I haven't got the link yet, but I will update with the link. The whole point with this paper is that the iterative ensemble smoother, the way it has been used in reservoir applications, are solving everything in the state space. And that leads to really complex pseudo-inversions of huge matrices, the size of the state dimension. And the methods are quite unstable numerically. So what we tried to do was to reformulate everything in the ensemble subspace. And that's because we know that the posterior solution is supposed to be contained in a space spanned out by the initial ensemble. And that we can show. So in that sense, this new method is not giving a different result or an improved result compared to the standard iterative ensemble smoother, but it's doing everything in a nicer formulation and a much more stable numerical implementation. And okay, let's just make some definitions. So I have the prior ensemble in blue, that's my X. I have an ensemble of measurement perturbations. And I should also say that this work is highly inspired by the iterative smoothers by Sakov and Bouquet, who did this for the square root methods. But it gets a bit more complex in the derivations here, in fact. So I could compute the mean of the data and the ensemble members. You have the ensemble anomalies A, and you have the measurement perturbations E. So what you do here is that this is subtracting the mean, and I have scaled them with square root of n-1. So that my covariance is just, ensemble covariance is this one and this one. It might be hard to remember all of this, but again, we have the cost function, and we make this change of variable where we there are different ways of doing this. In fact, in the paper, we assume that this solution is given by the mean of the prior ensemble plus a linear combination of anomalies. But I like better this formulation where I have the prior realizations plus this linear combination. So now what you estimate now is this vector W of, if you have 100 realizations, it's 100-dimensional vector. So you want to find these coefficients to compute the update. If you put it into the cost function, you get a cost function that looks like this. And what you see now is that this big matrix is completely eliminated. You just have a covariance, which is the identity in this case. And yeah, and this is just the likelihood term. And then we can compute in the normal way the derivative and the second derivative. So you get the gradient and you get the Hessian like this. If you put these together in a Newton formulation, then you have this one divided by this one as the update term. And I'm not going through all the derivations. It will take too much time. And you get an iteration that looks like this. So you have the update of W is the previous value or estimate of W plus a coefficient times this delta W. And that delta W is just this term here. So you have this is the Hessian here. And you have the innovation term plus this extra matrix here. OK, so the problem now is this term here. Because this is the derivative, the tangent linear operator of your model evaluated at the current iteration for each realization. And it's not obvious how to do that. Again, you can use adjoints to compute it. But what we do is that, yeah, we write it like this. The first thing we do is that we define this term using a joint or common G for all the realizations. We are not going to use individual gradients. We have one gradient for all the realizations. And this G is defined by, formally by a linear regression, like this. So that means given these covariances, G is defined. So you replace G with this linear regression. So now the model, tangent linear model, is disappeared. We only have covariance matrices. And we are in a subspace formulations. We have less realizations than the dimension of the problem. So we introduce pseudo-inversions. So this is just, or ensemble covariances. So that's the approximation here. OK, so we have this covariance bit CYX and the CXX in here. And if you use an identity, we can write it like this. So here we have the model prediction is Y. The centered model prediction is Y. And then we get the pseudo-inverse of the whole state matrix. And this is the problem. Previously, we actually computed this. And yeah, it's quite numerically unstable in a way. But what we can show is that if we define a transition matrix from the initial anomalies to the anomalies at iteration I, then we can replace this A with AI times omega inverse. Okay? And then we can show that this product disappears in all but a trivial case. If your model is linear, then this one disappears. If the model is nonlinear and you have a larger state space than the number of realizations, it disappears. Only in the case when your state space is less than the number of realizations, you have to retain it. But that's a trivial case, because in that case, this is so small that it's easy to compute. And that means you can devise an algorithm that has no reference to the state matrix or state ensemble at all. You have the initial inputs is the ensemble matrix and the perturbed measurements, and possibly the error covariance matrix for the measurements. You set double U1 equal to 0. You compute the model prediction, subtract the mean, and scale it. You compute this omega matrix. you solve for S here. It's just linear systems to solve. It's quite easy, and the dimension is the number of realizations again. And you compute the right-hand side, and you have this equation for the iterations. So you see that in all of these equations, you don't really refer to the model ensemble. You are in a subspace formulation, so everything is reduced to the ensemble size. The biggest computation is, of course, the final update, because you have the state ensemble, you have to multiply it with the transition matrix. But then all these other computations are linear in the number of measurements. And I'm going to show some examples of how to solve this inversion in an numerically efficient way. Just to show you an example, this is the same model I solved before, but I used only 10,000 realizations because in this case I have to solve this system of 10,000 by 10,000 equations. So this method is not suitable for really high-dimensional problems. But I start with the prior. I get the first update, second, third, fourth, fifth. So after 5 iterations, I have essentially converged. And since this is independent of the state dimension, you will have similar convergence for a high-dimensional atmospheric model. There is, the only thing that can impact the convergence is the nonlinearity of the model. Yes. So let's see how, and this is actually, there are some old results I want to present now. It's something I published in 2004. And if you look at this expression here, or we can use Woodbury, and you get it in this form, which is similar to what a number of other operational schemes are using. So you have to compute the inverse of the measurement error covariance matrix. And the simplest way to do that is to assume that it's diagonal, because then it disappears and you get this simple matrix to invert, which is the size of the ensemble. Okay, so, and it's stable. So that in the case with a diagonal error covariance matrix, and you scale it with the standard deviation of the measurement errors, you get this simple equation. But now you have neglected correlations between measurement errors. And what I want to do is to solve this problem, allowing for general representations of the measurement error. And then in 2004, we published a scheme where we, I wrote this question here. Why are we inverting a matrix with the size, the number of measurements, when we only want to solve for 100 coefficients, the number of realizations? Right? Because that's what we are doing, and it's not clear that we have to do that. So what we did in this case was to, we wrote a singular value decomposition of this S, which is the model predictions. You write it like this, and then you do some, put these things, the U and sigma outside the parentheses, and then it turns out that what you effectively is doing, and you introduce a pseudo inversion of the sigma plus here, is that you project the error covariance matrix onto the ensemble subspace. And if you continue from here, you end up with a really simple equation where the inverse of this one can be written as this product here. And this inverse is just a diagonal matrix. And so you can compute this inversion quite efficiently. The biggest computation is up here, because you have to multiply with this m by m, the error covariance matrix. So in this case, it's m squared times the number of realizations. But then we are using ensemble representations of the prior. Why can we not also do that for the measurements? And if we do that, then we formulate exactly the same algorithm using the measurement perturbations to represent the error covariance. So of course we introduce some additional sampling errors by doing this, but it's not clear if you have a reasonable sized ensemble how big these errors are. In this case, we get an algorithm which is linear in the number of measurements. And in particular, in the applications I'm working in now, this becomes really important because we get so much data. It's like we have big four-dimensional seismic data coming in regularly, and we have to process this efficiently. But again, if you replace the error covariance matrix with this product, you get exactly the same derivation. You project the perturbations onto the ensemble subspace again, and you do the inversion like this. And that means it's lunch. Yeah, it's lunch. Yeah, yeah, okay. And just to show a little bit some examples. This is from a reservoir case again. And I just want to show that I'm minimizing many cost functions. I'm plotting all the cost functions, and you see that in this case, after 4 or 5 iterations, it's converged, I would say. And also we choose there's an issue with Gauss-Newton methods because ideally you could use step length equal to 1, which would try to find the minimum immediately, right? And in the linear case, it converges exactly. But when you have ensemble methods, you have an approximate gradient, and you have to reduce the step length a bit because for some realizations you might actually deteriorate the results because the gradient is not good enough. And you see it here. I think in this case I have 5 realizations where I actually increase the error between iteration 1 and 2. But I try to tune it so that most of the realizations are converging. So then I'm not making a choice if I should accept the result or not. I just always accept, but I have a short of step that in general it converges quite fast. But then I've been doing one example here. It's still a diagonal error covariance, but I used the different schemes. And so I have this IES 0, which is the exact one. I have the first one where I have an exact error covariance, but I use the subspace inversion. And I have the last one here where I use the ensemble representation of the measurement errors and together with the subspace inversion. And this is the average value of the cost function. And essentially it gives the same convergence, the same results. So based on this, there is no reason that we should not use the fastest one in a way. And this is just one example where I look at 1 or 3 different parameters. It's a scalar parameter in the system, which is a fault multiplier. It says something about how much oil water would stream across or through a fault. But we have a prior, which is this one, and then the 3 different schemes give these 3 columns here. So these are exactly the ensemble members. And you can see that they are all more or less giving the same result. And if you look at the prior and the posterior oil production from 2 different wells, so yeah, the blue is prior, red is the updated, and these are the 2 different schemes, the simplest one and the exact one, and the same here. You can see they all give almost indistinguishable results. So this is kind of making a case for using these approximate subinversion schemes to simplify the numerics. There are some references in here. And this, everything I've done is part of my project, which is called DigiRes for digital reservoirs. And we have the Research Council, and I have 7 oil companies investing into ensemble methods, which is quite good. So what I've been presenting, we have seen the duality of the data assimilation and the inverse problem. Iterations improve the estimate for weakly nonlinear models. Iterative methods allow for inclusion of general model errors, which is quite important because that I didn't know a year ago. I presented a new efficient and simple iterative smoother, which kind of makes these methods more accessible in a way. And then the last one, ensemble subspace inversion, allows for correlated measurement errors, which is also quite important. And with that, I actually managed within my time. It doesn't happen often, but